Time and Space. Let's continue with Zoran the Dragon narrating Time and Space, understanding the relationship between time, space, and mathematics. Greetings, fellow explorers of the universe. Today, we embark on one of the most fascinating journeys yet into the very fabric of reality: time and space. These two concepts are deeply intertwined, shaping the universe in ways that are both mysterious and beautiful. So, as we soar through the stars, I, Zoran the Dragon, will help you unravel the secrets of how time and space connect, and how mathematics gives us the key to understanding it all. What is space? Let's start with space. What exactly is it? When you look up at the sky, space might seem like an empty, endless void. But in reality, space is much more than nothingness. It's the stage where the universe plays out its cosmic story. It's where stars, planets, and galaxies exist, and where light and gravity weave their way through the cosmos. But here's the thing: space isn't just something that objects move through. According to Albert Einstein's theory of general relativity, space itself can bend, stretch, and warp, depending on the objects within it. Massive objects like stars and planets actually curve the space around them, creating what we call gravity. It's as if space is like a flexible fabric, and when something heavy sits on it, everything around it shifts and moves. What is time? Now let's turn to time. We often think of time as something separate from space, like a river that flows in one direction, from the past into the future. But time, just like space, is part of the very structure of the universe. And as Einstein showed us, space and time are not separate at all. They are part of a single entity called spacetime. Imagine spacetime as a four-dimensional fabric, with 3 dimensions of space: length, width, and height, and 1 dimension of time. Events in the universe don't just happen in a location, they happen at a specific time as well. This means that time and space are linked together in ways we're just beginning to understand. The speed of light and time dilation. Let's dive into something truly mind-bending: the connection between the speed of light and time. In our universe, nothing can travel faster than light, which moves at an incredible 299,792 kilometers per second. That's about 186,282 miles per second. But here's the strange part: when something moves close to the speed of light, time itself begins to slow down for that object. This is called time dilation. Imagine you're flying through space at nearly the speed of light. From your perspective, time seems normal. But if someone were watching you from Earth, they would see your clock ticking more slowly. This effect has been confirmed by experiments with fast-moving particles, and even with astronauts who spend time in orbit. For them, time moves just a little bit slower compared to people on Earth. Gravity and time. The twin paradox. Gravity also affects time. Remember how I said that massive objects like planets and stars bend space? Well, they bend time too. This means that the stronger the gravitational field, the slower time moves. For example, time moves more slowly on Earth's surface than it does in space, because Earth's gravity is pulling on the fabric of spacetime. This effect is known as gravitational time dilation. The famous twin paradox helps illustrate this. Imagine 2 twins: one stays on Earth, while the other travels on a spaceship at near light speed. When the space-traveling twin returns, they will have aged less than the twin who stayed on Earth. The closer the traveler gets to the speed of light, or the stronger the gravitational field they experience, the greater the difference in their ages. This mind-boggling reality was proven by Einstein's theories and tested in real life by experiments like those with atomic clocks in planes and satellites. The curvature of space and black holes. We continue our journey. Let's take a look at one of the most extreme examples of space and time bending: black holes. These are regions in space where gravity is so strong that not even light can escape. When a massive star collapses at the end of its life, it can form a black hole, pulling everything around it into an incredibly dense point called a singularity. The space around a black hole becomes so curved that anything: stars, planets, even light that comes too close gets trapped. The boundary around a black hole, called the event horizon, marks the point of no return. Inside the event horizon, time itself can slow down to the point where it almost stops relative to the outside world. If you fell into a black hole, from your perspective, time would pass normally, but to an observer watching you, time would seem to stretch out infinitely. The expanding universe and cosmic timing. Let's zoom out to the biggest scale imaginable. The entire universe. In the early 20th century, astronomer Edwin Hubble discovered that the universe is expanding. This means that galaxies are moving away from each other, and the farther away a galaxy is, the faster it's receding. This expansion of space is like stretching a balloon. Every point moves away from every other point as the balloon grows. But what does this mean for time? As the universe expands, time itself stretches along with it. The Big Bang Theory tells us that the universe began as an incredibly hot, dense point about 13.8 billion years ago, and has been expanding ever since. So, in a sense, time began with the Big Bang. As the universe continues to expand, time as we know it keeps ticking onward, but the rate of expansion could even affect how time behaves on the largest scales. Einstein's field equations, the mathematics of spaciometry, understand the relationship between time, space, and gravity. We turn to one of the most profound equations in the history of science, Einstein's field equations. These equations describe how matter and energy affect the curvature of spacetime, which in turn affects the movement of objects within it. Simply put, mass tells space how to curve, and space tells mass how to move. The field equations are at the heart of general relativity and are used to predict everything from the orbits of planets to the behavior of light near massive objects. They're also crucial for understanding phenomena like black holes, gravitational waves, and even the expansion of the universe. Conclusion: the dance of time and space. We return from this incredible journey through time and space. Remember that these two concepts are forever linked. The universe is not a static place, it's a dynamic, ever-changing dance of objects moving through curved space and flowing time. From the bending of spacetime around massive objects to the expansion of the universe itself, mathematics allows us to unlock the mysteries of how time and space shape the cosmos. Through the eyes of Zoran the Dragon, we've seen that time and space are not just abstract ideas, but the very foundation of the universe itself. With every moment, we are part of this grand cosmic dance, moving through a fabric of spacetime that stretches and bends in ways that both astound and inspire us. This chapter unites the scientific facts of spacetime with the narrative magic of Zoran the Dragon, creating a compelling and educational story for all ages. With careful attention to mathematical and physical truths, the journey through time and space captivates both the imagination and the intellect.